AI agents excel at writing isolated functions, but without systemic understanding, they routinely break complex real-world software. Currently, the industry standard for how these models navigate a repository relies on iterative, text-based search. Developers call this grep and read. The flaw in this approach is structural. A code base operates as an interconnected network of dependencies, but text-based search treats it like a flat, unstructured document. When an agent attempts to trace a single dependency chain, it executes a search command, reads the resulting file, extracts the specific reference, and triggers another search. Repeating this loop and read cycle rapidly consumes hundreds of thousands of tokens for a single prompt. As the context window fills with irrelevant boilerplate and raw text, the agent begins to lose track of the original instruction. As context vanishes, the probability of error increases. The agent may reference a non-existent API or fail to account for a critical test case that has been pushed out of its immediate window. This points to a significant architectural mismatch. By relying on unstructured retrieval for structured logic, we are forcing the model to reconstruct connections that should be deterministic. This benchmark measures the mismatch. The traditional Explorer agent burns 10,000 tokens, while the Graph agent uses just 1,000. For tool calls, the Text Explorer requires double the API interactions. Latency is even starker, 30 seconds of processing versus a fraction of a millisecond. The engine driving these metrics is CodeBase Memory, an open-source tool designed to give AI agents a photographic map of a project's architecture. It works by abandoning flat text entirely. It ingests the raw source code and converts it into a queryable property graph. To bridge the gap between this external database and the language model, it utilizes the Model Context Protocol, or MCP. Instead of searching for string matches, the agent uses standardized MCP tools to ask direct structural questions. It can query exactly which module calls a specific function without reading a single line of raw code. Offloading the structural mapping to an external graph database realigns this efficiency trade-off. The model no longer has to choose between exhaustive exploration and saving its context for the actual reasoning task. Mapping a 50,000-node repository deterministically requires exact precision. Relying on regular expressions to extract logic at this scale guarantees failure. The pipeline begins the parse phase by deploying TreeSitter, a parsing system capable of reading 66 different programming languages. TreeSitter strips away all syntax formatting, whitespace, and comments to generate a strict abstract syntax tree. Specific elements from this tree are extracted and transformed into distinct, isolated node types in the graph, representing the functions, classes, and enums of the project. The system then maps relationships between them by drawing directed edges, linking caller to callee. The parser also matches cross-service HTTP routes. This bridges logic across boundaries, mapping an API call in a Python backend directly to the express route that catches it. Because dynamic routing creates uncertainty, these cross-service connections are assigned confidence scores ranging from 0 to 1. The parse phase takes thousands of flat text files and successfully outputs a highly structured, relational map of developer intent. But extracting the AST is only the first step. The hardest algorithmic hurdle occurs during the build phase, call resolution. When the parser finds a raw text string representing a function call, the system has to prove that string matches one specific, uniquely qualified node in the graph, out of potentially thousands. To solve this, standard function calls pass through a 6-strategy cascade funnel. The first layer checks the file's import map. If prefix and suffix matching align the call with an explicitly imported module, it assigns a 95% confidence score and establishes the link. If the early strategies fail, the token drops to the fourth layer. Here, the system queries a project-wide reverse index, searching for a uniquely named match anywhere in the codebase. This string-based cascade is highly efficient, but it completely breaks down on languages utilizing pointer indirection, implicit scopes, or method receivers, like C++ and Go. To accurately map these complex architectures, the system deploys a specialized LSP-style hybrid type resolver. This resolver ignores the raw strings. Instead, it evaluates expression types bottom-up, tracking exact variable bindings and unwrapping pointers in memory before it allows an edge to be drawn. Flawless call resolution is mandatory. If the engine creates a single false link, the LLM will hallucinate a dependency that doesn't actually exist in the code. Once the edges are resolved, the system hits a data bottleneck. Writing millions of individual nodes and connections directly to a hard drive is far too slow for local development. To accelerate this, the engine spins up a parallel worker pool, utilizing pthreads-based atomic work stealing to process extractions simultaneously across multiple CPU cores. Instead of writing to the disk, these parallel workers push their data into temporary in-memory buffers. Only when all extractions are complete does the final fleshways occur, merging the buffers and executing a bulk insert into a single SQLite write-ahead log file. There are no heavyweight external vector databases to configure. The entire operation runs through a zero-dependency, single static binary. But live codebases are not static. A graph built 10 minutes ago is obsolete the second a developer saves a new file. To maintain accuracy, a background file watcher monitors the directory using adaptive polling. By computing XXH3 content hashes, the system identifies and successfully re-indexes only modified files in under a millisecond. Pairing in-memory buffering with incremental single-file SQLite storage creates a local knowledge graph fast enough to keep pace with live developer workflows. Granting AI agents direct access to a local repository introduces a critical, often ignored risk regarding host security. When developers install opaque third-party binaries, they are executing code with the host agent's full file system and network permissions. A compromised model context protocol server can silently exfiltrate proprietary source code or establish persistent backdoors across an entire engineering team. Codebase memory implements a defense-in-depth approach to establish a baseline standard for safe MCP deployment. Before deployment, an 8-layer CI audit suite scans the source code, flagging dangerous C library calls and hunting for embedded base64 payloads. At runtime, the system enforces strict sandboxing, stripping meta characters from shell arguments to physically block injection attacks. At the database level, SQLite authorizer callbacks actively intercept and block malicious attach or detach statements before they reach the engine. Finally, the release pipeline mandates deterministic build provenance, forcing the binary through more than 70 distinct antivirus engines before publication. As autonomous agents gain deeper system access, rigorous deterministic binary verification must transition from an afterthought into a foundational industry requirement. We can measure the practical impact of this architecture by looking at the benchmark data across all 31 tested programming languages. The MCP graph proves vastly superior at cross-file structural queries, hub detection, and caller ranking. The graph structure enables algorithmic analysis like Louvain community detection, which partitions the call graph into functional architectural clusters on demand. However, the study identifies a specific limitation. The traditional text exploration agent still wins when a prompt requires exact line-by-line code replacement. This is an intentional engineering trade-off. The graph discards exact source string lines to maintain a low storage footprint and sub-millisecond query speed. Vector embeddings and retrieval-augmented generation attempt to bridge this gap, but semantic similarity cannot substitute for hard, deterministic structural edges. The data points to a clear conclusion. The optimal architecture for next-generation AI coding agents is a hybrid model. By utilizing structural graph retrieval for instantaneous, repository-wide navigation and falling back to exact text search only for localized editing, we bridge the gap between language model reasoning and complex software architecture.